Hey guys, it's Miss Miklos, and in today's lecture we are talking about limits at infinity. I love this picture. This is the guy's feet. It looks weird. Anyways, so we're going to see what is the limit of a function as it approaches infinity. And that makes it very different from some of the other limits we found. We've been able to use a lot of graphs and be able to use direct substitution, and today that's not really going to be the case. So let's just take a look at this graph here. Okay, we can see this is the function f of x equals x plus 1 over 2x. And this is what we call the horizontal asymptote, which is y equals 1/2. And back in Algebra 2, some of you guys may have spent some time finding the horizontal asymptotes of rational functions. And the reason why this asymptote is important is because, remember, that's a line that our function is getting close to but doesn't actually touch. So as we continue to the right, it's going to get really close to wherever this asymptote is, but not actually go past it. So what we find is that our limit to the right, so to positive infinity, is 1/2. And the same thing is true as we go to the left. It is also 1/2. Okay, so based on that logic, and here it says these limits mean that the value gets arbitrarily close to 1/2 as x decreases or increases without bound. Okay, so it's just saying that as x continues to go to infinity, it's getting really close to 1/2. So using that info, can we predict what we think this limit's going to be and this limit? So I'm actually going to zoom in here. There we go. And the one thing that I noticed on the other one, it was kind of like we took these coefficients. So I'm going to say the limit as x approaches infinity of x plus 1 over 3x is equal to 1/3. And that's going to be a little preview of something we're going to learn later. In this case, I could go ahead and take those coefficients. And I'm going to write out my proper notation here and say it is equal to 1/4. Now, that's actually how we learned to find the equation of horizontal asymptotes. So that's why the limit is going to be at those values, because those are the values that we're going to get super close to as we go to positive infinity and as we go to negative infinity. Okay, so even though this just says infinity here, if we put a negative out in front, we would get the same exact answer. Okay, so the following definition is going to be super, super important for us today. So it's telling us if r is a positive real number, then the limit as x approaches infinity of 1 over x to a power is equal to 0. Notice it is true also if it goes to negative infinity. So if I have 1 over x squared, 1 over x cubed, 1 over x, this is always going to be 0. We also need to remember some of the properties we learned back in 11.1 and 11.2. And the first one I want to point out is when we just have the limit of c as x approaches infinity. This is just a constant value, so it's really saying it's like a horizontal line. So our limit is going to be that y value, which is c, because that is the anticipated height as we approach that value. Okay, so we're going to use that info as we get into number 1 here. So it says find the limit. So what we're going to have to do here, we're going to do this algebraically first. I'm going to have to use some of the properties that we learned back in 11.1. And one of the first properties we learned is that if I'm finding the limit of a binomial, we said that we can actually split this up into 2 different limits and subtract them. Now, the other thing that we learned is that if I have a constant value, I can go ahead and it's kind of like we're factoring it out. We're putting it out in front of the limit. So in this case, I can split this up, so I'm finding what is the limit of 4 as x approaches infinity. And I know that answer is 4. And then what is the limit of 1 over x squared as x approaches infinity? This is the new concept that we just learned, so this would become 3 times 0. So I get the limit as x approaches infinity of 4 minus 3 over x squared is equal to 4. Okay, so some problems are going to be that straightforward. In fact, now it's asking us to go ahead and look at a graph of this function. So I'm not going to go to my graphing calculator, but you guys should go ahead and graph this in your graphing calculator. And what we're going to see, okay, if this is 4, we have a graph that kind of goes like this, where we can physically see it's getting close to y equals 4, but it's not actually going to touch 4. Okay, we could go ahead and look at our table. We could look at values all the way out here to see what's happening as we get closer to infinity. Regardless, we are going to see, though, that it appears that the height is 4. Okay, so the method that we're going to use for finding limits at infinity, and you know it's very important when we use 2 exclamation marks, but what we're going to do here, we need to divide the numerator and denominator by the highest power term in the denominator. Okay, and the reason why we're going to do this is going to enable us to use those properties we just talked about. If I have something like 1 over x or 1 over x squared, the limit as we approach infinity of that is 0. Okay, so for example 2 here, we have 3 different problems, and we're going to find the limit as x approaches infinity for each of these functions. So for a here, I'm going to write the limit as x approaches infinity. And the first thing we said we need to do is we need to look and see what is the highest power term in the denominator. And the highest power term here is x squared. So I'm going to divide everything by x squared. So I have negative 2x over x squared plus 3 over x squared over 3x squared over x squared plus 1 over x squared. Okay, so if we want to, we can be really technical and use all those algebraic and limit properties that I showed in the previous problem. But I'm going to kind of just simplify this as is. So this is like negative 2 over x plus 3 over x squared over 3 plus 1 over x squared. I'm going to look at all of these limits separately because we know that with our sum and addition, we can go ahead and do that. With our quotient property, we can do that as well. Even though this has a 2 out in front, I know the limit of negative 2 over x as we approach infinity is going to be 0 because we have this x in the denominator. My next term is also going to be 0 because of this in our denominator. Over the limit of 3 is going to be 3, and the limit of 1 over x squared as x approaches infinity is 0. So I get 0 over 3, which is 0. So I'm going to go ahead and say the limit of f of x as x approaches infinity is 0. Okay, so every single time here, we're doing the same thing where I'm going to go ahead and I'm dividing by the highest power term in our denominator. Okay, so if we look at part B, this time the highest power term in my denominator is x squared. So I'm going to have the limit as x approaches infinity of negative 2x squared over x squared plus 3 over x squared over 3x squared over x squared plus 1 over x squared. So I'm going to go ahead and simplify this and say the limit as x approaches infinity of negative 2 plus 3 over x squared over 3 plus 1 over x squared. And once again, I'm going to look at these separately. So the limit of negative 2 as x approaches infinity is negative 2. The limit of 3 over x squared as x approaches infinity is 0. The limit of 3 as x approaches infinity is 3, and the limit of 1 over x squared as x approaches infinity is also 0. So I get here that my limit is negative 2/3. So I'm going to say the limit as x approaches infinity of f of x equals negative 2/3. So we're seeing this concept itself is not that tough. It just gets pretty repetitive. Number 3, once again, I notice that the highest power term in my denominator is x squared. So even though I have a higher term in my numerator, I'm dividing everything by x squared. So when I simplify this, I get negative 2x plus 3 over x squared over 3 plus 1 over x squared. And when I find those limits, something really weird happens here. That negative 2x tells me that as our x values increase, this decreases without bound. Okay, and the reason being, it's like if x is 100, I get negative 200. If x is 1,000, I get negative 2,000. It's continuing to decrease, and sometimes we'll see where it continues to increase, so it's not approaching a unique real number. So what we're going to say here, because of this, I didn't mean to draw that, but it looks like an L, so I'm going to use it. The limit as x approaches infinity of f of x equals d and e, because it does not approach a unique real number. Okay, so even though this isn't that bad, it can be a little time consuming. So the great news I have for you is that we have a shortcut. Okay, basically it says when the degree of the numerator is less than the degree of the denominator, our limit's going to be 0. When the degrees are equal, the limit is the ratio of the coefficients. And when the degree of the numerator is greater than the degree of the denominator, the limit does not exist. And we kind of, if we look back here, we can see that. Okay, so for part A, I notice it's bigger in the denominator, so our limit's 0. For B, they have the same power, so I'm going to take the ratio of their coefficients, and I get negative 2/3. And for C, I notice I had a higher term in our numerator, so our answer was does not exist. The great news I have for you, we can use the shortcut every single time. I do not need to see all this work anymore. We can just skip to actually writing out that shortcut. Okay, so this is a bunch of technical stuff that tells us why the limit exists and when it doesn't and all of that. Honestly, we don't really need to worry about that today if we just remember the quick shortcuts that I just talked about. Now, if you guys care, that's just something good for us to know. Okay, so number 3, which we have a lot of space to do because that's really the only problem here, I'm going to use our shortcut. So I'm going to look and see where is the highest power term, and it looks to me like we have the same exponents in my numerator and my denominator. So I'm going to look at these terms, and I need to take the ratio of those coefficients. Okay, so I'm going to go ahead and write this out. And I get that our ratio is negative 3/2. Okay, just a reminder, if the higher term was in the denominator, so if this was x cubed, our limit would be 0. If the higher term was in our numerator, so if this was x cubed, then we would say the limit does not exist. And this is how you can do your homework tonight. Okay, so are there any other ways to evaluate limits at infinity? And the answer is yes. Evaluating a limit algebraically gives us exact values, but like we saw back in sections 11.1 and 11.2, tables and graphs often give us very reliable estimates as well. Okay, so in your homework tonight, in your suggested problems, it's going to look kind of like this, where you might have to use a table and use the graph and go ahead and use it algebraically, so doing a little bit of everything. So the first thing that I would do here for our table is I would go ahead and put this into our graphing calculator. So then I went to my table setup and I put it in ask mode, and I've already demoed that to you, so I'm not going to go to the calculator right now. But when I put in those values, I get 0.2, 0.9615, 0.9996, 1111. So based on that table, I would say the limit as x approaches infinity of x squared over x squared plus 4 is going to be equal to 1. Now, if I sketch a graph of this, okay, so I'm going to go ahead and look at my graph. The graph looks something like, here's one, okay, and it looks something like this. So we can kind of see as we continue to the right, there is a horizontal asymptote of 1, so once again we get that same limit. Algebraically, okay, if I'm finding the limit as x approaches infinity of x squared over x squared plus 4, remember we look to see who has the highest power, and they're the same here, so I'm going to take the ratio of their coefficients, 1 over 1, which is 1. So that's how we can go ahead and use a table and use a graph just like we've done previously. I personally think algebraically is the easiest way, but these ways work as well. So our last problem, we're going to talk about finding an average cost. And that's kind of a common thing where it's like if we sell so many of one product, how much are we actually does it cost us to make each product? So it says you are manufacturing cheesy greeting cards for Mother's Day that cost 50 cents per card to produce. Your initial investment is $5,000, which implies that the total cost C of producing X cards is given by this following cost function. The average cost per card. We use this C with a line over it to be average cost, and that means that I'm taking the cost and dividing by the number of cards. So it says find the average cost per card when X equals 1,000. So I'm going to say the average cost would be 0.50 times 1,000 plus 5,000 over 0.50. So this is just something that I can go ahead and put into my calculator, okay, which I'm going to do right this moment. So I'm doing 0.5 times 1,000 plus 5,000 Sorry for my delay here. Hopefully you guys are following along on your calculator. And then dividing by 1,000. And I end up getting 5.5. And quite honestly, that is really high for the cost of a single card. Now, for part B, it says we want to find the average cost when X is 10,000. Okay, so this time I'm substituting 10,000 in. Oh, and I made a mistake here. That should not be 0.50. I don't know what I was writing. That was 1,000 because that's how many cards we had. So if your number wasn't matching mine, that is why. Okay, so here I'm dividing by 10,000. And when I put that all in, I end up getting 1. Okay, next, the average cost when it is 100,000. So what I'm predicting here is that this cost is going to continue to kind of decrease here. And I end up getting 0.55. So we're seeing that it's continuing to decrease. Now, based on this logic, we might think that, okay, well, if I do 1,000,000 cards or 1,000,000,000 cards, that this is going to continue to go down. But there's actually a limit as we approach infinity. And if we go ahead and find the limit as x approaches infinity of 0.50x plus 5,000 over x, we know that we just need to look and see where is the higher denominator, or the highest term, I mean. So if we look, we have x's here, so I can just do 0.50 over 1, which is 0.50. So we can see that we're actually pretty close to the limit here. When I produce that many cards, they're going to end up costing 50 cents per card. So hopefully you guys just, the biggest takeaway today is when we are approaching infinity or negative infinity, if the highest power term is in both the numerator and denominator, we take the ratio of their coefficients. If it is in the numerator, the limit does not exist. If it's in the denominator, our limit is 0.